All right, I need to cut these steel rivets out of this steel. This is a bed frame. It's a little hard to store. I've been scrapping a lot of stuff. I scrapped, I guess, 2 basketball goals. I'm thinking about using one of the basketball goal backboards as part of a desk, maybe for like a gaming setup. Not really a basketball fan, but might be an interesting thing to sort of work up into selling. So anyway, this is from a bed frame. These sort of slide together, but these are steel on steel rivets, so they're a little difficult to get off with regular tools. These hole saws will cut they're annular cutters. They allow you to avoid using hole saws, but they will cut through steel. They can be mounted on a drill press, which I should be using because that allows your cutting to be like perpendicular and uniform. But I don't really have that. It also allows you to control the RPMs for the material, which is kind of important for not damaging these things. You also don't really want to drop it, because if you drop any cutting tool, it's going to ruin it. It happens to everybody's, Fisher Price, my first router bit. Anyway, so I also have this Craftsman radial saw, and I was sort of taking it apart because it's heavy and hard to move. But it has, I think, 5 different axes of, or 5 different parameters to its, configuration space, which describes like the dimensions and constraints where a device can move. So it's useful for robotics, but it's also useful for mechanical engineering. And so this allows some device to move along the arm, but you can also adjust the yoke, which you may be able to see down here. And that allows, I think, 2 radial axes of movement, or 2. So anyway, you can move it up and down on the y-axis, back and forth on the z-axis. You can move the arm. You can rotate the arm, so that's 1 angle and 2 linear parameters, and then you have 2 other angular parameters, I believe, on the yoke. So that just kind of is what it is. And after scrapping a lot of things and then realizing I've wasted a lot of time, what I do value is modularity. So right now I'm using one of these, one of these systems from Amazon that has UNC threads, which is used for camera equipment. So if you have a tripod, it probably has UNC threads. Very adaptable, very modular. You can even mount a projector with it, apparently. So trying to figure out how to get this lumber rack set up, and I used a projector and wrote an SVG with HTML and CSS that was just a repeating grid, and I was sort of able to use the projector as a laser level. So if I 3D printed something that would allow me to have a level, like a bubble level, sort of attached to the device, would be much easier to get it to work. But then I realized I could just mount it to a tripod. And with some kind of 3D printed bubble level thing, it basically functions as a laser level. Though you do have to have something like a Raspberry Pi or some kind of computer to run a browser, or you need to be able to run a command in Linux that displays a image in a terminal, which requires KMSCon. No love for KMSCon. It doesn't actually require KMSCon, but you don't really want to look at anything else. So anyway, the annular cutters, there's this lube that is recommended to use. It's just a stick, so you take your tool and you just put the lube in there. You get it kind of on there, kind of want it on there. The lube's really important from what I've heard. I don't really know what I'm doing, so just keep that in mind. I do know enough to know that I should use a drill press, but I don't really have one here. Basically I just need to, I'm just going to run through what it's like to take one of these rivets out and explain how the process works. This is like way more convenient than the other methods for removing the steel rivets. And if you're going to use any kind of like scrap steel for framing, you really kind of have to be careful, because if you damage it in some way, it's not really the same thing that it was before you damaged it. So that's something that I kind of lack, is like the awareness of like I lack a sense of proportionality for like how some kind of design needs to like handle the load. So I tend to want to use very strong things. I like steel because steel is modular. I can just cut holes in this with these annular things and these annular cutters, and then I can just bolt it together. Eventually I'd like to be able to weld it together. That is an adventure for some other time. And that like designing something to account for load with welds is complicated, because you have to make sure that you're welding so that you're joining the surfaces of the metal, and you have to be aware of like the axes that are being joined and how the weld sort of transmits the load, and then your technique needs to sort of allow that to be accomplished, and it matters a lot. But anyway, so I'm just gonna kind of run through this. It's pretty easy. You just use this hole punch thing, or this punch pin thingy. Really use some guidance here. Open up iPhone Edit, which is awfully convenient. I will admit, it really is. Anyway, so to get started here, I just need to find the center of the rivet, and like I was saying, when you're joining these things together, when you're using scrap materials, you have to be really careful, because like steel, you don't ever want it to get wet. So if it's gotten wet, just probably throw it away. Really using any kind of scrap materials is just kind of stupid, because like, you know, you might have to remove nails or staples from wood, and like, what if you missed one? Well, if you never use scrap materials, you don't ever have to worry about that problem. But now you do. So anyway, so it's just kind of really important. You kind of really want to know. But anyway, I have these dreams of going to Burning Man and fucking welding things together and doing cool shit. Anyway, so it's gonna be loud. I just need to get this hole sort of started. Got to be in the center. Oh yeah, and so when you remove the rivets, if you do it the wrong way, what's gonna happen is that as you're like, if you use just a normal drill, which is gonna eat up your drill bits, it's actually gonna cause like it's gonna cause the steel, which is constrained by the rivet hole. It's going to cause the steel to puff out and deform and push against the hole and make the hole like, it's going to deform the hole, which means that like when you go to put another bolt through there or whatever, then it's not really making good contact with like the head of the screw, the fastener, and everything. It's not really making flat contact with the entire surface, which is like, you just don't really want to have to worry about that. So if you do it this way, what you're going to do is you're going to remove the head from the rivet by cutting into it until you see this little like washer pop up. And at that point, you've cut through the rivet cap. And then you'll have the other part of the rivet. You just tap it out. It's a little bit tough, but you just tap it out. I got to do about like 30 of these, and then I'll have some nice angle iron that is free. And it's also sort of teach me about doing stuff like this. So like in the future, this will be actually more useful for just like making holes in steel and then being able to join it together however I want. And I like steel. I really prefer aluminum, but I like steel because it has like when you're designing stuff with wood, like if you need it to you know, encounter different circumstances or encounter different usage patterns, different patterns of load, you might make a desk and you're going to arrange your monitors differently, or you might have a lot of books on the desk or something, and they might move around. It's a little bit hard to predict how like that's going to actually strain the desk. And then ultimately, like the storage space that you have remaining when you use wood, like the volume is much smaller than were you to use like steel or certain kinds of design patterns like structural pipe, or let's see, the tensegrity kind of like tension furniture and tension shelves. Those have their own like kind of quirks. So each of these design patterns or methods of design, like wood versus steel versus structural pipe versus cable tensioning, they each have their own kind of pros and cons and like suited uses. But when you're approaching the design of something like shelves or furniture or whatever, you kind of want to like make things simple and easy to kind of index. Like if you have features like like nooks for like different books and stuff, like it's nice when they're uniformly spaced, because you can just really quickly reason like about like, oh, those books didn't fit there, so they don't fit in those other 5 evenly spaced things or whatever. Like it just relieves some like what do they call that, like computational burden or whatever. Anyway, so like nice uniform simple design makes it so that like the features of the design just kind of disappear. You don't have to think about things as hard. Like, because ultimately you're doing something to support some other kind of activity or endeavor, and like that's the thing that you care about. Like I don't really care about like a desk or whatever being what it is. I don't need a Herman Miller chair or whatever. Like I'm doing that so that I can do whatever I want on a computer, and like ultimately so I don't really have to think about the desk. Like so like when things are simple, they're like flexible, and they can support a lot of different kinds of activities or behaviors or whatever. They can support a lot of different patterns of usage, and like good design just kind of like fades into the background. This is why like you don't really know good ergonomics until you've dealt with bad ergonomics. Like you just don't. And it is like, it's something that it depends on like your psychological kind of like characteristics or quirks or idiosyncrasies or whatever. But like, so people with ADD might be more affected by bad ergonomics than people without ADD. But it could be catastrophic. Yeah. So, and they're like those, like when you're like fitting out an office with furniture, and those are decisions that you're gonna make like once, maybe every 3 or 5 years, and like you don't really have time to be like, hold up, hold the phone, we're gonna move all the furniture around and buy new furniture. Like it's expensive, it's hard to really justify. You don't really want to justify, or you don't really want to have to revisit previous decisions made by an office manager or by yourself as an owner or whatever that were bad. So like you don't really want to talk, like you don't really have that kind of opportunity to redesign how you're going to arrange your office furniture, and the structure of like these things in an office actually make a really big difference. It creates like regions of interaction, or for your employees, you might have employees that have roles where they need to focus more, they need more separation, or and so like, but you really just want something simple that makes the most of whatever you're using. So if you use steel or preferably aluminum or something like that, you get like, if you're building a bookshelf out of steel, which probably looks ugly, you're gonna get like more volume of storage space, or like if it's a desk, you're gonna get more volume of like shelf space or drawer space for the same kind. Like, so you have a space that contains the thing that you built, and then inside that thing that you built, if it's a desk, you have space for drawers and this and that. But then if you want to maximize the amount of usable space, then you want something that's stronger. And wood is very modular, but it has its own quirks. Steel is modular. Structural pipe is modular. It's nice because you can just be like, oh, this projector has UNC threads. Like, I can just use a tripod. Like, I don't need to worry about the projector mount that I bought where I can't find the lock screw or the lock bit or whatever to like undo the screws. Like, it's got UNC threads. Like, and then like you can 3D print all kinds of stuff, and then the UNC threads just eat into the 3D printed part, and so that holds itself together. So like, you know, like you would probably want to print those threads in there, but like basically like it's really easy. Like if there's like different types of modular design patterns that are like, or different like sets of like parts and systems that lend themselves to modularity, and it's like just like those are the kind of parts that you want to scrap. So like, yeah. And it's just like interesting because like for me, like the scrapping and stuff, it sort of tells me about the telos of the design, which is like kind of answering like the why behind the design. When you go to school and stuff, they teach you about the how, but really answering the why is like kind of tough. So like there's the Silicon Valley people have like the 5 whys exercise, and that's really an exercise in like, you know, higher order thinking and like thinking about like the telos or like the real ultimate purpose of something, so that you can figure out like, okay, are we going directly at what we want, or do we need something else, or is there something that is like a little bit higher order that we're not really conscious of yet that's going to be relevant later. But trying to just like most of the telos of things, it like fits together in a way that is like difficult to describe in words often, and it's often sort of left out. Like you're left to figure that out by yourself. So they'll teach you things in, you know, like on like online courses or YouTube videos. This is how you do it. Well, like, okay, like, well, what if I want to do something where like I need some part of what you've done? It's like 20% of what you've done, but 80% of it is like open-ended. Like, do I just repeat what I saw in the video? And then like, how do I do that? Why do I do that? And the telos of like processes is interesting, because like, so like, why do I approach organization in a certain way? Or why do I do this? Or why do I like, there's answers for this stuff, but it's like difficult and, to really put into words. And then it also sounds a little bit pompous, because like if you're trying to explain like really why you're doing something, it just sounds like, you know, you know what I mean? Anyway. I guess that should be good. These bits have like a little pin in them that like keeps everything sort of straight. I'm gonna like sort of fix the motion by grounding the vibrations into my elbow, trying to make this perpendicular or the orthogonal. And the vibrations are just sort of telling you like what's going on. So you can sort of feel when it's not cutting right, and like you just kind of want to read that kind of feedback. You should just use a drill press, because then you don't have to worry about it. It's kind of nice. And I don't really know what the RPMs on this drill are, but it seems to indicate that I shouldn't be using RPMs of greater than 1200 on the little chart. And that's 60 per second, and I don't see this thing moving more than 60 rotations per second. So I'm just gonna go ahead and back off and check it. I'm gonna look at the tip of the bit with a loop. These things were like $80. It's a lot of money to me. So I like to look at things under a microscope or look at things under a loupe, using a jeweler's loupe, because it's like, it's almost like seeing another dimension or whatever. Like you've got your X, your Y, your Z, you've got your surface, and then like, but you're not really seeing the surface like closely enough to really understand what's going on. Whereas like if you look at something using a microscope, it's telling you all this, it's giving you all this other information, just like the vibrations. Like there's these, it's information. And I read some reviews of these annular cutters, and it said that some people seem to be indicating that they break, but I think you just have to pay attention to your feeds and speeds, and don't drop the things, because they often have ceramics, and ceramics are very hard but very brittle. So like the second that you drop it, it's broken. Now if I drop it on wood, it's not going to do anything. Washer thing. Whew. All right, now there's gonna be some loud banging, so, and I'm not sure that these nitrile gloves are really gonna hold up to all this stuff. They're like 15 mil or something. I was gonna use it for oil painting. I don't know if they're 50, they might be 5 mil. I don't know what a mil is, but they're more mils than the other ones. So like if I was gonna paint, I'm gonna paint with like, or I would like to paint in the future. I would like to use oil, and when you're like considering what your palette's going to be, you kind of have to pick a team, either team organic pigments or team inorganic pigments, because like you have to like, and I don't really want to use quinacridone magenta, which is kind of like, that's kind of hard. I definitely don't want to use dioxazine purple, and so you're kind of like limiting yourself, and it's like kind of hard to figure out how all this stuff fits together. And the more I think about it, the more it seems like you just got to pick inorganic or organic. You want to use some organics where they make sense, but really like inorganic pigments are just like brighter, truer. Their spectrum, their reflection spectrum is like a little bit more narrow sometimes. And then there's just lots of interesting things to kind of learn about how the world works, because we didn't always have LCD monitors with ICC calibration profiles, so we couldn't always produce all the colors of the rainbow. So anyway, enough about the pigments. It's just really interesting. There's also like a lot of other stuff that you can learn about the world based on like pigments, because people spend a lot of effort like trying to figure out how to get new colors for their art and their architecture and their stuff. Like, cause yeah, you can source different minerals from different places. There's different kinds of chromium oxide that's like, like sourced from different regions of the world, and has like subtle different like tonal variations, and it's just, there's a lot of interesting stuff there, a lot of history. Anyway, so I'm just gonna try to bang this thing out, and I guess that's kind of like all I have to do here. But oh yeah, physics, I forgot. Lever arm, it's useful. It's really helpful actually. I was just my video cut out, so yeah, I'm gonna try to remember what I actually said, which is sorry for the rambling, but I think it's interesting. Being a polymath kind of sucks, by the way, or trying to be a polymath. I don't know what I'm doing, because you end up having to like organize like all these different like physical things into all these different like, you have to make sense of all these things you want to do all the time, and you don't have enough time, and then like that actually itself ends up like sort of like forcing you to It's complicated. Yeah, I can't get this thing out. Oh, not good. All right, yeah, so as you can clearly see, I don't really know what I'm doing here. So like, I guess like what I was gonna do with this table saw is like figure out how to like, I don't know, like I've got a lot of ideas, but 1972, they when they sold you something like a radial saw, they would put the blow up diagrams in the manuals, which is actually super useful because and they would like list the table of parts that you needed, because they actually expected, that their consumer would want to go to a hardware store and buy replacement parts, because they thought they were buying something that they were going to use for 10 or 20 years. So everything is much more maintainable. They distinguish the parts that you can buy from a hardware store versus the ones that you can't. All the information is front and center. It's just really interesting to see how like the specific design elements and all the parts sort of orient themselves around the configuration space. So you've got your y-axis that allows you to move the radial saw up and down, and then you've got your z-axis that allows you to move the saw back and forth, and then you've got your I guess I'll call it theta that allows you to rotate the saw and hit different angles, and then you've got the yoke, which is your phi 1 and phi 2, that allows you to sort of achieve like a second and third angle, I think, for cutting everything. And so like all the different like parts in the blow-up diagrams, like you can just sort of see how everything pulls out. Like you'll have all these like series of like washers and screws and nuts, or all these features will just sort of be like hanging off like the axis, like almost like a facade, or almost like they are like the facade that's hanging off the ideal of the configuration space. And it's just really kind of interesting. So I can replace some of the parts and put something like 3D printed on it or whatever, that, but then it's still retained. Like, I mean, it's a little bit too heavy to really expect to be able to do much with it. But it's interesting to think about. But I'm trying to figure out like what I would actually use it for. So it's like close to like maybe it would be able to be a CNC machine or something. I don't really know, but it already has like the ability to like maneuver between those different points in the configuration space. So yeah, which is a Riemannian manifold that has holomorphic kind of like things in it. So holomorphic constraints are like, you have like I guess the prototypical example is like a robot whose configuration is constrained by the motion of four structural members, like four like bars, and you can move, and there's an angle between each of the bars, and the angle always has to add up to 360 degrees. And so like some of the holomorphic constraint allows you to sort of like solve the equations better. These are things that I've always wanted to learn that I just haven't had enough time to really learn. So there's this like Northwestern University modern robotics book that accompanies a series of YouTube lectures, and you take a class on Coursera. But like when I want to take a class on Coursera, like you get out of it what you put into it. So like if you put a lot into it, like, so you can get the certificate or whatever. And I don't really like their certification programs or whatever. Like there's just like all these courses on there that are like, like, but at the same time, there's all these courses from like just like a wide array of like universities across the world, like for free. And and so the textbook like has all these additional things in it, and then, like, that's a good textbook for robotics. Another good textbook for robotics is the FRC textbook, which starts off with some basic linear algebra, then progresses into Laplacian transform and Z transform, and solving for the Like, so it goes from linear algebra to like defining what the state space is, and then like doing state space stuff to figure out where your poles are, which are the interesting points in the interesting points in the state space. It's been kind of a while, but anyway, so like as your system is trying to maintain equilibrium or attain some objective, and you're trying to figure out how to attenuate the electrical signals to the attenuate and modulate the electrical signals to the motors and yada yada yada. You need to be kind of aware of these like, yeah, you have to deal with like the Laplacian transform is just like a really mean thing to do to anybody. But it's interesting. So like thankfully it moves on from that and then starts talking about the world space. The modern robotics textbook also covers like the world space, which is just like, so you've got like a robot, it moves, it has like motors, you know, that allow it to move in these directions, in those directions. So like, and then there's just like all these like weird, like kind of like mathematic things that you encounter where like, you're trying to like coordinate the activity of the motors to accomplish movement through a space where there's obstacles to the space. And so like, it's pretty amazing. But like for me to really, really, really be able to learn this stuff, I need to program. And yeah, I don't have like enough hardware to do it the way that I would want to do it. The ideal way is that you have like a server rack with like a Jupyter lab server running on it, and that thing has access to GPUs. So you could just use Kaggle, which is nice to know, like 6 years too late or whatever, however many years too late, that you could get free GPUs on Kaggle. That's nice. It just really makes me feel like, like I probably should have encountered that information somehow. You know what I mean? But I didn't. So I just always believed that I couldn't do anything because I didn't have a GPU. But anyway, so you have a server, like a rack server, and then it has GPUs that you can sort of like add to a running lab notebook. And I would just rather have it be local because yeah, if I was doing stuff in the cloud, like it would, like I would easily get to $1,000 a month, like just easily, like and maybe even $2,000 by accident, right? So, but like running the stuff at home like means that you own the data and all this, you know, whatever privacy, blah 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 blah. But also it just means that you could do a whole lot more, and it's kind of frustrating that we don't have ARM servers for us home labbers. Like that really sucks. Anyway, so yeah, I just got to do this like 20 more times, and then I'll have the angle brackets, and I might be able to use them to make a something. I have no idea.